welcome to the Signal Path. In this episode, I wanted to show you a wide variety of millimeter wave and microwave components which you may come across when doing high frequency measurements in the lab. One of the main reasons why I'm making this video is to help newcomers learn how to treat and how to handle and how to identify these type of components so that they won't get damaged in the lab. These things are very expensive, they're built with very specific tolerances, and if you don't handle them properly and don't follow proper procedure when using them, you can actually either totally damage them or you can change their performance, and which don't directly result in you making measurements which are not optimized. And you don't know whether it's your measurement, your circuit that's a problem, whether it's your components that are the problem. To avoid this type of ambiguity, you have to follow a very strict procedure when using these type of components. So I have connectors, cables, amplifiers, biases, a whole bunch of stuff here right behind me. And we're going to go through every single one, show you what they look like, and some of them we're going to take apart so you can see what they look like inside and understand actually how these things work besides just using them in your setup. So hopefully by the end of this video you're more familiar with what type of components you're using in the lab, and that would directly result in better measurements and less damaged components in the lab, which of course nobody wants. So let's get started. So here I have a table showing a whole bunch of different connectors. You can download this document and all the other documents I'm showing throughout this video directly from my website. So on the left you can see a whole range of different connector types, and some of the more familiar ones are listed like BNC and SMA. It also shows you the upper frequency range that is supported by each of these connectors, and I'll explain that later. As well as the coupling torque, which is the torque required to tighten these connectors and attach them together. We'll talk about that as well. And here on the right side it tells you whether that both male and female sexes of the connector are available, as well as whether you can buy different grades of these connectors from Agilent. So this is a table directly from Agilent. So there is metrology, instrument, and production grade connectors. So what does that all mean? What's the difference between them? So metrology grade connectors are the highest standard of connectors. They have the tightest tolerances, they support air dielectric interfaces, and we'll talk about that, and they should only be used for calibration or for very, very sensitive S parameter measurements. And you should not use metrology grade connectors for day-to-day uses where you're not doing a very, very sensitive measurement. Metrology grade connectors are the most expensive, and they also have the highest manufacturing tolerances, meaning that you have to make sure that you always connect a metrology grade connector to another one of the same grade. For example, if you mix and match metrology to production grade, because the production grade connectors don't have as tight tolerances as metrology, you can actually damage the metrology grade connectors. So you should always use each class only within itself and never mix and match them in order to make sure that they have the highest life. Instrument grade connectors are also very good, but they sit in between production and metrology. So here you're doing somewhat sensitive measurements. They have fairly tight tolerances, they have very good performances, and they last a long time, but they're not as good as metrology grade. Now production connectors are the most common, and they have a limited number of uses you can do with them because they're not built with the highest standard. After a certain time you have to throw them away because they don't last very long, but they're cheap and you can buy them in in larger quantities and use them around the lab. So make sure that you always use the grade of the connector that is suitable for a task at hand, and never mix and match them. So let's take a look at some of the familiar connectors which we've all seen. So let's take a closer look at the BNC connectors. Here is an example of that. I'm sure you've seen many of these. This is a T-junction where all three terminals of this connector are connected together. It has a male and two female connectors on each side. So here you can see that the BNC is rated up to 3 GHz. So that means that after 3 GHz, this BNC will not maintain its design characteristic impedance. Remember that every time you use millimeter wave or microwave connectors, they have to maintain a characteristic impedance that matches the instrument or matches the circuit that you're trying to measure. Most of the time that's 50 ohms. Most high frequency equipment have a 50 ohm port at all their high speed ports. So this means that after 3 GHz, because of the dimensions and because of the dielectric material used in a BNC connector, the characteristic impedance of the connector will no longer be 50 ohms. So another mode of excitation occurs within the connector, and it can actually change from 50 ohm. It could become capacitive, it could become inductive. Either way, it will not maintain a nice predictable 50 ohm characteristic impedance. So if you try to pass a signal through this that has frequency content above 3 GHz, for example, then the connector will not be 50 ohms and you're going to get a really weird response, frequency response. You could get reflections, you could get unusual attenuations, you could get notches in your frequency response. Either way, it was going to give you trouble. So you cannot really use a BNC above 3 gigahertz. And anyhow, this one is intended for very low frequency. Anyway, this is not a 3 gigahertz BNC connector. So you have to also be careful with that. Just because it's BNC, it doesn't mean it's going to work all the way to the rated 3 gigahertz. Another very common connector that you see all the time is, of course, an SMA connector. An SMA connector can work all the way up to 18 gigahertz. So if you purchase a high quality, high frequency SMA connector, it's good all the way up to 18 gigahertz. And one of the most characteristic features of an SMA connector is this white ring that you see inside it as this dielectric. The dielectric of an SMA connector is Teflon. And it's very clearly visible when you look inside the connector. This is a connector, of course, and this is actually a converter where it converts an SMA directly to a BNC. Now these type of converters are really common where they go between different types of connectors, and we'll see more of them. But what you have to be careful with is that as soon as you do this, you're limited, of course, by the frequency, maximum frequency operation of the one that has the lowest frequency of operation. So even though an SMA can work up to 18 gigahertz, as soon as you convert it to a BNC, now you're limited to 3 gigahertz frequency of operation of the BNC, and you can no longer use it above that. These converters are used all the time because sometimes you have something that has an SMA interface, but you need to connect it to a BNC. Of course, these combinations of all possible combinations exist. Now, if we go and look at even higher frequency, then we start getting into air dielectric compatible connectors. We have 3.5 millimeter, 2.92 millimeter, which is also known as K. Then we have 2.4 millimeter, 1.85 millimeter, and 1 millimeter. This dimension represents the width of the dielectric from the center of the connector itself, and I'll show you that. Now, you have to be very careful here because of the nature of these connectors and because of the manufacturing reasons and compatibility reasons, you cannot connect any connector to any other. And if you try and they're not intended to be connected to each other, you can actually completely damage and break the connector. Now, 3.5 millimeter and 2.92 millimeter and SMA are thread compatible, meaning that if you have, for example, the SMA connector that I was showing you, such as this one, this is thread compatible with a K connector. For example, this one. So you can screw in this SMA connector directly to this K connector and they will fit together. But that's not recommended because you have to keep in mind that the tolerances required to build an SMA connector are not the same tolerances that are required to build a K connector. And this is because the K connector tolerances are much tighter. They require much more precise machining. And therefore, if you try and connect an SMA to a K, you could end up in a situation where the SMA is at the edge of its tolerance limitation and it doesn't fit within the K connector anymore, and as soon as you try to screw them together, the center pin of the SMA, for example, can break the center pin of the K connector. So even though they're thread compatible, it is not recommended for you to connect an SMA to a K connector. However, a 3.5 millimeter and a 2.92 millimeter connector, you can use interchangeably. You can connect them together. A 3.5 millimeter connector can work all the way up to 33 gigahertz, and a 2.92 millimeter or a K connector can work all the way to 40 gigahertz. And this is why it's called K, because K band goes all the way up to 40 gigahertz. Now, if you want to go between 2.4 and 1.8 millimeter connectors, now the thread actually changes, meaning that they cannot be physically screwed into each other. And if you're not careful, you're going to damage the connector. So let me show you a converter so you can get a good idea. This is an unregistered connector. This is actually a metrology grade connector. It's a very, very expensive, couple of $100s for one of these. So be very, very careful with them. On one side, you can see that, look how small this dielectric is. This is actually a V connector. So this is a 1.85 millimeter connector that can work all the way up to 65 gigahertz. And if you look, as soon as you look at it, and as soon as you have seen enough connectors, you can immediately distinguish which one this is. You can see how small and tight the air gap is, and the center connector you can see in the middle. And if I look on the other side, you can see there's a huge difference. The gap is much wider. This is actually a 2.92 millimeter a K connector to a V converter. So this converts a V female to a K female. And you have to double check every time you want to connect something to really make sure that you're connecting the right components together. Now, another way besides the center conductor that is vastly different between these two, if you want to distinguish them, look at the threads. There is a very clear difference between these threads, which are the V connector threads, and these threads, which are your K connector threads. They look completely different, and they're not compatible with one another. You cannot use one of them with the other one. So let me show you another converter. This is another converter that converts a V male, let me see, get this to focus, a male connector to a female K connector. Now if I hold this just right, you can actually see right through this connector. See if I put my hand underneath it, you can see right through it, and this is because the dielectric used in this is air. The center tap connector of this connector is sitting essentially with very thin plates of plastics, is kept hovering exactly in the center of this connector, and this is a very high quality connector again that converts V to K but of a different type. So you can see that when I was talking about an air dielectric, it really is completely filled with air, and except for those very tiny pieces of plastic that hold the center tap in place. This is also true for cables. So for example, if I show you a high quality cable, here's an example of a K cable, and if I look at the connectors at the end of the K cable, you can see that you can again see right through them. The dielectric here is air once again. So this is a K to K male to male connector. So this will work all the way up to 40 gigahertz, no problems. But if you go to instrument grade cables where people don't use air dielectric, you can actually get a different material dielectric. I'm not sure what this one is. It could be Teflon, but I'm not 100% sure. This is actually a V cable. This is a cable that will work all the way up to 67 gigahertz, but it doesn't have an air dielectric connector. Instead, it uses some other dielectric material, but it is a V connector. So this is, for example, a good day-to-day use cable. And just because it's day-to-day use doesn't mean it's cheap. This is probably costs maybe about $200. So these are not cheap anyway. So now let's talk about the procedure to screw these connectors into each other. So you have to be very cautious because you have to follow a very careful procedure when you connect connectors or cables to each other. For example, let's say that I am interested in connecting this V compatible connector, this 1.85 millimeter cable, to this 1.85 millimeter connector. So you would be tempted to just connect them and screw them together, but what you have to make sure of is that you have to make sure that you don't turn the body of the connector and that you only turn this nut. And this is because when these connectors get screwed together, the ground, which is that metallic flat part, has to come in contact with the metallic flat part. Basically, the outer shell of the cable has to connect to the outer shell of the connector. And if you allow this connector to turn while you're screwing them together, those two surfaces eventually end up rubbing against each other and wear each other out. And even worse, the center pin of the male connector, when it is in contact with the center pin of the female connector, if you allow this to continue to turn, they will rub against each other and they will wear out, and you can age the female center connector of this particular one, and that's also very bad for the connector. So what you want to do is you want to have a way of holding on to this connector without allowing it to spin. So a good way to do it is to have a wrench. All of these connectors have a body that's actually has an indentation like this one that will fit within a particular wrench. So this one can be held in here very nicely. So you hold this with your hand, making sure it doesn't spin, and on the other side you take the cable very carefully and perfectly centered. You see, for example, right there I was attempting to connect it to the wrong side. So be very careful. I noticed that I was doing it the wrong way because I recognized that is the correct thread. So let me flip this over, like so. So make sure that you're perfectly centered, place the connector inside, and gently turn it. If it's not turning really easily, then it's not done correctly. You never need to force any of these connectors, because all of these connectors are precision machine grade, and they will fit in perfectly within each other. If they don't, you're doing something wrong. So at this point, I'm holding this wrench in my hand, and this connector cannot turn, and I have hand tightened it as much as I could. And now I move on to the torque wrench. And here's an example of a torque wrench. This is a Hewlett-Packard one, and these torque wrenches are tuned to a particular torque. You can see that the tip will actually bend as soon as it reaches the correct torque. So I will now at this point place this, and now I'm holding the other wrench with my hand. Now we'll continue until the wrench is bent. And now this connector is tightened to the proper specification. And now you should never over tighten it, and you should never have it too loose. If you just hand tighten it and forget about it and don't use the torque wrench, the interface between the connector and the cable, or the connector to another connector, is not going to be perfect. And you're going to have impedance variation, reflections, notches in your frequency response, which you don't want. And of course the process of removing it is just the reverse. You place the connector into the wrench, use the torque wrench, unscrew until it's loose enough, and then you use your hand and you gently remove the connector and you separate them from each other. The other thing you need to make sure of is always make sure you examine the connectors before and after you've used them. Make sure the pins are perfectly centered. Make sure the connectors are completely clean. There's no dirt or debris in there. If, for example, the center pin of the male connector is bent, throw the cable away, because you should never use it with another connector. If this center pin was bent and I try to screw it into this connector, I will end up damaging this connector also, and they'll both have to be thrown away. So be extremely careful when you do that. Another thing very important about millimeter wave and microwave cables is that you should never bend them too much, and you should never bend them unnecessarily, because as you bend them, the characteristic impedance of the cable can actually change. You can get a little bends that are, if the bend radius is too tight, you can damage the dielectric, you can damage the center tab, and the characteristic impedance will change, and they will be no good anymore for measurements. So be very careful. Don't bend them. Don't unnecessarily put them in weird position. Make sure you protect the part where the cable connects to the connector. Treat them very, very gently, because they are very sensitive and they are very, very expensive. And if you break them, especially in a university environment where these things are already very hard to get because the budget is so tight, if you break it, you can actually delay your own measurements or delay another graduate student's measurements for months before one of these things can be purchased again. Sometimes it's also possible to get cables that do conversions of different types of connectors for you. So this cable actually converts a K, which is this one, to a V. Now you can see right away that the dielectric of this one, which is the white one, is much wider than the dielectric of this, which is the black one. This is, again, doesn't use an air dielectric, or it doesn't use completely air, because the dielectric, it has some tiny holes in it, but it's not just air essentially. So this converts that. So be careful when you pick up a cable. Examine the center tab. Make sure you know what type of connector this is. Here's some other quick little examples. Here's essentially a 2.4 millimeter connector conversion. I believe this is actually a DC. This is actually a DC coupling cap. And yeah, we'll come back to this one. I have another through here. This is a through connector, very high grade. This is a precision, again, metrology grade connector. You can see right through the connector again. This is a 1.85 millimeter female to female connector. Again, very, very expensive. So be very careful. And I also have, of course, a 1 millimeter connector to show you, a 1 millimeter cable to show you. So this is a broken cable. You can see the other end of it is broken. I've removed the connector so you can see what it looks like. But here's the center tab. Take a look at this. You can see that the center tab has a 1 millimeter dielectric. This cable will work all the way up to 110 gigahertz. This connector is extremely fragile. You have to be very, very careful with it. It doesn't use the same torque wrench as this one, because it has a different size actually. So you have to have the proper torque wrench for 1 millimeter connector. Even that torque wrench itself is a $500 or so. That's how expensive these things are. And this cable was made by Agilent. At a time, something like this would have cost a few $1,000s easily. So, and you can see on the other side, if it will focus, I don't know how easy it is to see, but you can see the center pin is tiny, very, very small. So Anritsu actually has a new connector for their network analyzer, which is even smaller, is 0.9 millimeter, that will work all the way up to 140 gigahertz. And I think they're working on a 0.8 millimeter connector for even higher frequencies, but that's not very common, and only they're making it at the time, I believe. You can also get a 1 millimeter cable that converts directly to a V on the other side. And again, this cable, now this is a rigid cable, so when you bend it in a certain direction, it will always stay there. Rigid cables are really good for S parameter measurements because you bend them in one orientation and they're really stable. They don't move around. So the phase response of the cable is very stable as you try to do your measurements. But the thing about rigid and semi-rigid cables is that once you bend them in a direction, if you try to unbend them and bend them in a different way, you actually damage their performance. So really, if you have a rigid cable and you need to bend it, make sure when you bend it to a certain way that you will always use it in the same way. You can't really reuse those. They're very good. They will give you stable measurements, but only once they're basically set in their place. So this is one that I've taken from the lab. Again, so because it is ending in a V, this particular connector will only work up to 65 gigahertz, even though on the other side of it you have a 110 gigahertz connector. So this cable is just a converting from 1 millimeter to V. So enough about connectors, let's look at some other microwave components. Another really common component is the termination. So this is a 50 ohm termination, and if you look carefully on it, it says this is an Agilent 85138A model, and this one is a 50 ohm termination from DC to 50 gigahertz. So as soon as you read 50 gigahertz, you would know that the connector would have to be at least 2.4 millimeter, and in fact it is. And this is a 2.4 millimeter connector, and you have to be very careful with these as well, because they not only have, so this is essentially just a 50 ohm resistor to ground, but it's not just any regular 50 ohm resistor. It's a 50 ohm resistor that will maintain a 50 ohm impedance all the way up to 50 gigahertz. That's a very, very difficult thing to achieve. So these things are also quite expensive. And when you use this, make sure that you don't put too much current through them. These are not designed to accept a lot of DC current. Also, there's a maximum power you can put into these before you heat up the resistor too much and you break it and it won't be 50 ohm anymore. So you have to be very cautious with these. Terminations are really widely used when you have, for example, a differential circuit and you want to terminate one output of your differential circuit while you measure the other one. So these things are used all the time for that, for those purposes. You can also have other things like attenuators. Here's an example of an attenuator. So again, if you read, this is a Hewlett-Packard one, model 3334040C. It's an attenuator that works from DC to 26.5 gigahertz, and it has 20 dB of attenuation. So you connect your signal in here, and the signal that comes out of the other side will have a 20 dB attenuation, but only if the characteristic impedance that is driving this and the characteristic impedance that this is driving are also 50 ohms. Remember, all these components are designed to work in a 50 ohm environment. And because this is only working up to 26.5 gigahertz, it doesn't need to have a very small connector. It's actually using, I believe this is a K connector, so it's rated up to 26.5 gigahertz, but it's using a K connector. So this is a 20 dB. You can get them in all kind of sizes, 6, 3, 12, all kind of different attenuation values. You can even make them custom made. Inside this is essentially a resistor, a few resistors that will divide the signal for you. Now there's other ways to divide the signal. There is two main ways where microwave circuits divide signal. So if you need to divide the signal power into two ways, so for example you put in a signal one way and then you want to divide the power into two ways, you can just use a T-junction like the SMA here. Because again, you have to think about this very easily. If I put 50 ohm on this side and I put 50 ohm on this side, then when I look into this terminal, I will not see 50 ohm, I will see 25 ohm, because this 50 ohm will appear directly in parallel with that 50 ohm. So then I will break the characteristic impedance of the system. This port will have a 25 ohm impedance, which is not good. So in order to maintain that impedance to stay 50 ohm, people do a resistive power splitter like this one. Here it is. Let me get the camera a little bit higher. There it is. So a resistive power splitter is nothing more than 3 16.7 ohm resistors. So 16.7 ohm, 16.7 ohm, and 16.7 ohm, just like this guy. You can even this model even actually tells you the value of the resistor right there. So these three resistors that you see here, the input and the two outputs, is the same three resistor, the input and the two outputs. Now, if you terminate all three ports into 50 ohms like so, when I put in power into this, it will divide evenly between this output and this output. But because these are resistive components, they will also dissipate some power. And therefore, this portion of the circuit will absorb some of the power and turn it into heat, and the rest of the power will be divided equally between these two ports. So a resistive power splitter actually has a 3 dB extra loss. So if I put 0 dBm power in here, minus 6 dBm and minus 6 dBm come out of here. The rest of that power is dissipated in there. If there was no loss, then you would get minus 3 dBm and minus 3 dBm. So if this thing loses power, why would anybody ever use that? Why don't we find a different way where we don't have to lose power? Well, a resistive power splitter has one major advantage, and the advantage is that it works down to DC. So the frequency of operation is extremely broadband. It can work from DC all the way to 67 gigahertz. In fact, I have another version of it here. This is a higher frequency version. This one works from DC to 50 gigahertz. So it actually uses this one actually uses V connectors, and if I look at this one does not use V connector, uses K connectors because it only needs to work up to 26.5 gigahertz. These are also extremely expensive. You have to be very careful with them. So because of the fact that they use resistors, they are able to go all the way down to DC at the cost of an extra 3 dB loss inside the circuit itself. Well, what if I don't want that? What if I don't need to go down to DC and I only need to divide the signal between a certain frequency range? Well, that can be done. There you have to do it using microwave techniques. Here's an example of another divider. Again, the signal is put in here and the two outputs are there. And this one, someone has written at the back that this works from 0.1 to 1.5 gigahertz. So if I were to open this, I don't expect to see the 3 resistors because this does not go all the way down to DC, but the advantage is that ideally if I put 0 dB in here, I only get minus 3 dB attenuation. There's going to be a little bit more because the microwave components has a bit of loss, but it won't have the loss of a resistive divider. So I've taken the cap off of this one, and you can see the microwave traces. Now I'm gonna have a totally separate tutorial where I go over microwave design and all these, what do all these lines mean, how do they work, how do we design them. But for now, the only thing we need to worry about is that if you look at this signal, it's connected to this trace at the top and it's connected to this trace at the bottom, and these two traces have 2 small resistors that are in between them. This is actually a multi-segmented Wilkinson divider, but we'll get into that later. You can see the thickness of the lines change and so on, but you can see at DC, at very, very low frequencies, these 3 are actually all connected together. But that's not remember, that's not a 50 ohm environment anymore because these are all shorted together. So this thing does not do a very good job at low frequencies. And that's why this has a rated frequency range, but it only works between those frequency range. But between that frequency range, this thing will do a very good job at dividing the signal between from here into here without much loss. So you put in 0 dBm and you'll get approximately minus 3 and minus 3, as opposed to putting 0 dBm here where you get minus 6 and minus 6 because of the resistive losses of the power splitter. Here's another example. Again, this is another power splitter. This is a really broadband one. This one works from 2 to 26.5 gigahertz, and you can see it says minus 3 dB and minus 3 dB here, and this is the input. So when it says minus 3 dB, of course it's not going to be exactly minus 3, it's going to be a little bit less than that. So maybe minus 3.5 depending on how much loss this has. But from 2 to 26.5 gigahertz, this is an adjuvant part, is a really broadband, but you can see it starts at 2 gigahertz and it does not start at DC, unlike the other one, for example, that we saw here. This is also a 26.5 gigahertz divider, but it starts at DC. So this is resistive, and this one is based on microwave components. I can't open this because it's really well closed up, and it's a rather expensive part. But it's another example of splitting. Now, as soon as you start to split signal using microwave techniques as opposed to resistive techniques, you can actually do even other fancy things. You can introduce phase shift. Here's an example of that. You put in a signal in here, you terminate the other one, and the output comes 0 degree and 180 degrees. You can't do that with this. In here, whatever phase that is here is going to be the same phase here. So the phase will be 0 degrees here, and the phase will be 0 degrees here. You can't get 0 and 180 here. That's another disadvantage of a resistive power divider. But using other microwave techniques, you can actually get a phase shift. You can get 0 degree, you can get 90 degrees, or you can even get a custom one if you want. But the frequency range will be limited. This one will work only from 4 to 8 gigahertz, and it's called a 3 dB hybrid because it divides the power to 3 dBs on each side. So narrow frequency range, but fancy and interesting frequency phase response that you can achieve by doing things like that. There are other ways of dividing power. Here's an example of a directional coupler. Now a coupler essentially divides the power but not evenly between its ports. So you put in a signal and most of it comes out at the other end, and maybe a little bit of it comes out its third port. So this is taken directly from actually a network analyzer. So this is a coupler inside the network analyzer. This one works all the way up to 50 gigahertz. But an interesting example that I can take apart is this one. This is a really low frequency one, and if you look at it, it says minus 40 dB on one port, minus 50 dB on the other port, and it has an input which is well, the output, which is the antenna, and it has another port. So this actually uses type N connectors, and type N connectors can work all the way up to 18 gigahertz, but this is not rated all the way up to 18 gigahertz. So this coupler, when you put in some power through here, almost all of the power travels right down the center and comes out of the other side. but minus 40 dB attenuation on this port and minus 50 attenuation on this port. So if I put in 0 dBm here, minus 40 dBm comes out of here, minus 50 dBm comes out of here if on the return path. So on the forward path you get minus 40 dBm, and if I put in 0 dBm on this side, I get minus 50 dBm on the other port. This coupler is used to just have to sneak on the signal a little bit. If I want to just look at the signal just a little bit, I don't need to take half of it away. I will use a coupler like this. Now, because the attenuation is so large, it's minus 40 and minus 50, the construction of this is really interesting. So here it is. It is a little bit weird because the input and the output are directly connected to each other through this line, through this copper wire that's running in the center. This is the other port, and this is the other port, the minus 40 and the minus 50. And this distance between them is enough for minus 40 or minus 50 dB of the power to couple to this line. So this is all they've built. All they've built is they've calculated this distance, they've modeled the electromagnetic fields around this inside of this unit, and they figured out that at this distance and at this type of orientation, they're going to get minus 40 and minus 50 dB of coupling, and that's it. That's all they need to do in order to get a coupler like this. But this is because the attenuation is really, really large. And you can also do this using lumped approaches. This is another coupler that I actually used in the review of the Rigo spectrum analyzer. And if you look inside of that, this one is a little bit more unusual. First of all, it has an AC coupling cap here, and you can see it's got these ferrite pieces that are carefully placed at specific distances along this line, and at the very end there is a lumped component here that couples the power to this one. So I haven't examined this very carefully, but I believe this is uses a more of a lumped technique to do that. Another interesting thing to note is that the input side, the material they use to put this capacitor on it is ceramic. So they have a ceramic substrate here, but at the other side, this substrate is transparent. It's actually made of quartz. So they're using very high quality material on the other side to build the material that they built the circuit on top of. So the substrate material here is quartz with ceramic here. This is a very interesting coupler as well. Another really common component is a DC coupling cap. So this is an SMA, again we can tell because of this white Teflon dielectric. This is an AC decoupling cap, meaning that it's just a capacitor, it's just a series capacitor. And this is used to isolate DC from the instrument. So if I were to put in my signal here and my signal has some DC content, let's say it's an amplifier and it has a 3-volt output voltage. And the other side, I cannot connect this to some of the instruments because a lot of instruments actually cannot take DC directly. So by using a DC coupling cap in series, I'm able to totally separate the DC from the AC side. So this is very common. Another really, really common component is a bias T. So a bias T is nothing more than a combination of an inductor and a decoupling cap. So you can see even the circuit diagram is shown on this picosecond one. So between this port and this port, there is an AC decoupling cap. So the DC is separated. But there is an inductor on this side connecting to this port. So there is a short circuit from here to here, and there's an open circuit from here to here at DC. So you're able to either look at the voltage that is appearing on this node through this terminal, or you're able to apply a voltage to one side only and not to the other side. This is a very, very useful component used all the time if you want to measure the DC voltage you have, or you want to apply a DC voltage to an input of an amplifier. If your input of your amplifier needs some DC voltage to bias, you apply DC voltage here, you connect this to the input of your amplifier, you connect this to your AC signal source. So you're separating your AC and DC path. Now this may seem really simple, but it's actually quite complicated to make one. Let's take a look at what things can go wrong. So here's the schematic of it. Again, very simple. We have our inductor that's connected to our DC source, and we have our AC signal that is being applied, and then we have our termination or whatever instrument that we have on the other side. So the DC path is this way, and the AC path is this way. Now, what would be the best we can ever do? The best bias T is to use an infinite capacitance here and to use an infinite inductance here. So this inductor essentially is an open circuit as soon as you have any frequency above 0, and this guy is a perfect short as soon as you have any frequency above 0. But of course we can't build that. We can't build an infinite capacitor, an infinite inductor. So what we should do is we should use the largest inductor we can and the largest capacitor we can. But I wish it was that simple. As you increase the value of capacitances and inductances, their high frequency performance actually degrades. Now let me show you an example of why that is. Even though an inductor just looks like a simple inductor, its high frequency model is very different. Here's an example of a high frequency model of an inductor. Now this is actually a rather simple one. This is a very basic high frequency inductor model. They can become much more complicated. Now let's look at this. Here's your inductor that you're interested in. Inductor has some series resistance associated with it that's captured by this. So together they have the quality factor of the inductor. So you know that every inductor is made of some kind of a conducting material and that has some resistance, and that's this resistance is captured like this. But as soon as you wind inductors up, the coils are going to have capacitance to each other. So that capacitance is captured by this cross capacitor between the two terminals. So this is the one terminal of the inductor, this is the other terminal of the inductor, and you can see all these things representing various imperfections of the inductor. So series capacitance, capacitance between the coils. You can have a capacitance to some ground. This is a monolithic inductor in a semiconductor, but really the principle applies. And you have some RC network that represents the substrate behavior. You have some capacitance to the substrate. You have some capacitance directly to ground. Now all of these components, at low frequencies, these components don't really do anything. But as frequency increases, eventually these components begin to interact with the inductor itself. And it turns out that at some frequency, this inductor can completely resonate with the other components, and you won't get an inductor at all. It can end up looking like more like a capacitor, and at some point it can be completely open, and at some point it will be completely short. So it goes through all that. Now as you make the inductor larger and larger and larger, these components also get larger. So the high frequency behavior of the inductor gets worse and worse and worse. So then what do we do if you want to make a bias T? Well, if you want to make a really high frequency bias T, it means that you cannot use a single inductor. You're going to have to use a series of inductors that are getting progressively larger and larger and larger, so the frequency response suffers, but it doesn't matter because the small inductor at the beginning covers your high frequency performance. Then you have another inductor that covers a little bit lower frequency, and so on and on. And here the same thing, you can build a few capacitors. Usually they use one really good capacitor, but it's also I've seen using more than one. But really it's the inductor that's the main problem in this. So I have taken apart a really good bias T. This one is actually broken, so I've taken it apart. This is an SHF. SHF makes a really good DC coupling cap and bias Ts and so on, all the way up to 110 gigahertz. So this one works from 50 kilohertz all the way up to 65 gigahertz. This is a huge frequency range. Think about how many orders of magnitude difference there is between these. So from 50 kilohertz, any signal lower than 50 kilohertz will not go through this path anymore. So you have to make sure that if you're using this bias T, that you don't have frequency content below 50 kilohertz, and you don't have frequency content above 65 gigahertz. And because this is a 65 gigahertz bias T, of course it's using a V 1.85 millimeter connectors on both sides. There it is, you can see it. So this is the circuit diagram is shown here. So here's your DC path from here all the way to there, and here's your AC path going this way. And you can see it says that you can put it as much as 16 volts and 0.4 amps through it. If you put more than 16 volts in here, you will break this capacitor, and if you put more than 0.4 amps, you're going to break the inductor. So you have to be very careful. And if I were to open this, and we can take a look inside, you can see exactly what I was talking about. So the decoupling cap is actually in here, so we can't see it. It's built in here. I don't want to open that part, but there's a decoupling cap in there. There's an AC cap that would be this cap right here, is sitting right here. Now there is a series of inductors that are getting progressively larger and larger and larger. You can see on top of every inductor there is a surface mount resistor that they have put there in order to DQ the inductor, make sure it has the proper frequency response and it has a proper damping factor and so on. And if you look very carefully, you can see there's a pin that comes out, and there's a tiny little wire that connects to the first inductor, and second one, third one, fourth one, fifth one, sixth one, and so on. And there's some more resistors and capacitors in there to decouple everything and make sure it works. So even a very simple bias T like this one is extremely complex inside and is handmade. And these things are several $1,000s each, very expensive, but they work really well. And look at the thick shielding to make sure that this is nicely well shielded. There's no noise coming in and out of this thing. So very nice. It's a very, very nice bias T. And then another last example of a bias T here. So this one works from 45 megahertz to 50 gigahertz. You can appreciate how hard it is to bring this frequency down from 45 megahertz all the way to lower and lower. This is 45 megahertz, is already 1,000 times worse than the other one, because the other one was only 50 kilohertz. This is 45 megahertz. So if you have any signal lower than that, you cannot use the bias T anymore because it will go through its DC port. But again, this one, I haven't opened this one because this is a good working one, but because it's 50 gigahertz, it also has V connectors at the ends anyhow. But another weirdly shaped one, this is an HP one taken from an instrument as well. You can make other interesting passive components. This is a phase shifter that works from DC to 30 gigahertz. Now the best way to achieve phase shift is to change the physical distance between these two terminals. So how can that be achieved? So what I mean is that if I have a cable and I make a cable longer and longer and longer, obviously the delay through the cable changes and it will accomplish a certain phase shift. And if I have it in a controlled way, I can have a phase shifter like this one, which is controlled by this knob. I've taken this one apart. There we go. You can see inside it. Now if I turn the knob, you can see that that plate moves back. Let's say I move it all the way back, and the signal now has to travel a longer distance. So the signal has to come through all the way through here, goes through this wire and all the way back. And if I turn it the other way, I will shorten it. So now there is less distance between those two paths. So therefore the phase shift is less. But this is a very high frequency one. You can see it uses K connector. It works all the way up to 30 gigahertz. This is a very common way of making phase shifters. These things are very useful when you're dealing with broadband circuits, when you need to align, for example, a clock to a data, or you need to align two signals together. If you want to create a specific phase offset at a certain tone, these things can be used for that. Here's an example of something else that you can do passively. This is a tuner. If you have this, again, I will do another video on these type of things later, but by adjusting the distance between the conductor in these rods, these are like stubs, and you can actually change the characteristic impedance. You can see these things extend in and out, and by doing so, you can actually tune a certain characteristic impedance in here. So the signal that flows through here and goes out of there will see these stubs along the way, and you can create a certain frequency response or an impedance response that you want. There's a lot of different things you can do with this, but I thought it would be cool to show you that you can create that classic stub behavior by using a component like this. If you start doing things a little bit more actively using other types of pins that consume power, so an active, some type of an active component. This is an attenuator. Even though the function of attenuation itself is a passive behavior, just like I showed you. Let me see if I can still find that component. I put it in here somewhere. And yeah, that 26.5 gigahertz attenuator that I was showing you before. There it is. This one is just a combination of different resistors. You can actually get one that's programmable. So by putting a certain voltage on these, you can turn relays that are built inside this, turn them on and off, and get different attenuation. So I've opened this, and you can see that every one of these pins is connected to a relay. The relay is on the other side of this substrate. This is a ceramic substrate, and you can see the transmission line that is running right across it. It's a microstrip transmission line, and you can see that there's these little black pieces that you see. Those are different resistors. So different ratio of resistors get connected in and out while constantly maintaining a 50 ohm impedance. You can achieve different levels of attenuation. So you can hear this when it is working. And if you have a signal source, and sometimes you turn the power throughout the power, let's say you go from minus 30 dBm to 0 dBm, you can hear clicking sounds inside the source. That's something similar to this, where the attenuation is mechanically controlled. The advantage of using a mechanical relay is that it has extremely good repeatability, and it will always give you the same attenuation. But of course, it may not last as long because the relays are mechanical, so they can break down. So moving on to active components, you can make things that do frequency conversion. So this is a doubler made by Markey. This is a very high frequency doubler. It can double signals to beyond 50 or 55 gigahertz. You can see it says F on one side and 2F on the other side. So if I put in, let's say, 25 gigahertz here, I will get 50 gigahertz on the other one. This is a broken unit. it doesn't work anymore because someone accidentally put too much power into it and actually killed it. Now, what would we expect to see in this? Remember, this has no DC ports. It's purely powered by the RF signal itself. So what is an ideal thing to use in a situation like that? If you remember from one of my previous videos, when I did a tutorial on linear and nonlinear circuits, there I used a diode, and that's exactly what they do here too. But they use a very high frequency diode. So in the center of this, you can see a tiny little diode there, and on this side, you can see the signal path. So let me show you carefully. So the signal comes in here, and it reaches the diode. The diode will rectify the signal and create a second harmonic. And you see this tiny, tiny little copper wire? That's actually a filter. That someone measured that distance and measured the length and so on to filter out the signal and isolate the output to be twice the frequency. Even though it has a filter and it doubles and so on, this thing does not have a very good fundamental rejection. So ideal multiplier will not allow the fundamental tone to come out at all. So if you put in 25 gigahertz, you only want to see 50 gigahertz here. But in reality, you put 25 gigahertz here, and here you will see 50 gigahertz, but you will see some of the 25 gigahertz also. And the other interesting thing is that this is a path of the signal in and out, and the other side is the ground of the transmission line, and you can see they have tapered the ground of this is a ground line because it's connected to the body. You can see they taper the transmission line ground in order to create a certain varying characteristic impedance in order to match to the diode, so that this whole thing will be 50 ohm input, 50 ohm output. And yeah, we'll talk about this type of techniques in a different video, but this is a doubler, again, fairly common. People use them all the time. And oh, there's one thing I forgot to show you from the passives. You can also make filters. So we're back to doing one passive thing. I've shown this in a different video, but I'll show it here again too. This is a filter that I believe filters is a band pass filter between 2 to 3 gigahertz or so. But this is a very high quality factor filter, so you can see how large it is because it uses very, very large cavities. And if I were to open this, you can see inside it you got all these different cavities that are one in a row, and this distance between them is all fixed. But on this side you have this various length of screws that they have carefully screwed in and then cut to the proper length. So when you put this in here, the interaction between these poles into the cavity will create a certain frequency response, and you can model this in a 3D modeling tool, and you can calculate exactly how big these need to be and where they fit and so on. So if you this is carefully placed inside here, and it will fit between those poles that you saw, and it will create a certain frequency response, and we will talk a little bit about that in a different video. So back to active devices, you can also get mixers. So this is a mixer. You can see the LO port is here, the RF port is here, and the IF port is here, and this is a double balanced mixer working from 1 to 4 gigahertz. And I will have a totally separate tutorial on mixers because that's a very interesting topic itself, and I can talk to you about double balanced mixers and double sideband transmission, single sideband image reject, and so on, everything. We'll talk about it in a different video. But you can get components like this all the time, and this is a fairly low frequency one. You can get them all the way to much higher frequencies, and mixers are used especially at very high frequencies to bring a signal down to lower frequencies where you can connect it to some kind of a test equipment. So here's an example of an amplifier. This is it's the mini circuit one. The model number is ZFL 1000 VH. It's at low frequency, a gigahertz or so amplifier. I've taken the back of it off, and you can see how these things are made. Again, they're all handmade. This is a 50 ohm input, 50 ohm output AC coupled amplifier. So you can see that this is a biasing port, plus or minus 15 volts, which then goes through some resistor for protection. You can see the various inductors here, and there is an adjustable capacitor. So you can, by turning this screw, you can actually adjust the capacitance to tune this. So someone will tune this to a certain frequency because this is the matching network of the amplifier itself, and you can see the RF transistor right there, which is directly connected to the output. So this is very low frequency, so it's easy to build. But imagine people build these at much higher frequencies. There they don't use discrete components like that. They will directly use an integrated circuit where the matching network and the biasing and everything is already taken care of inside the integrated circuit, and then all you need to do is to connect to the input and the output of the integrated circuit itself. But this is interesting because it uses discrete components. Here's another example of it. I cannot take this one apart because it's fully sealed, but this is a 30 kilohertz to a 10 gigahertz Anritsu wideband amplifier, and actually has 28 dB of gain. It's a fairly nice amplifier, good for NRZ data communication application, and it needs a plus and minus 5 volt, and then it does what it's supposed to. So this is a pretty interesting one too, and because it uses, it works all the way up to 10 gigahertz, you can see it uses K compatible connectors. So be very careful when using these things. Now if you want to go even higher in frequency, then what do? Well, I told you that 1 millimeter connectors work all the way up to 110 gigahertz. So you can always use these all the way up to 110 gigahertz. But if you don't want to put up with the coax loss, because even though this thing supports 110 gigahertz, there's still a fair amount of loss in a cable like that. So you can use waveguide components, which have much lower loss than coax, but they have a limited frequency range. You can use a component like this one. This is an Agilent waveguide to coax converter. So let me take this piece off so you can see it. So on this side is a waveguide piece, and this is a WR10 waveguide, which is a W band, works from 75 to 110 gigahertz. And on this side, you have a 1 millimeter connector. So even though the 1 millimeter connector works from DC to 110 gigahertz, because of the frequency limitation of the waveguide, then this transition is limited to 75 to 110 gigahertz. Even though this looks like you would have a lot of loss, it doesn't. It actually has very little loss. The entire loss of this is probably about 0.1 dB. And it will give you 75 to 110 gigahertz both directions because it's passive. It can either go this way or it can go this way. And this thing will be several $1,000s. Very expensive because, again, because of the W band as well as the 1 millimeter connector. So be very careful with these things. They're quite rare. And of course, once you go to waveguide, then you can do anything you want. Here's another example of a coupler. Is the directional coupler for a waveguide, so the signal goes through this way and some of it couples to that side. So again, this is a slightly lower frequency waveguide piece. You can see because the waveguide opening is larger. So as the waveguide opening becomes larger and larger, the frequency response of course changes. And the number, the WR, this is WR10. If you measure this in inches, the last 2 digits after the decimal point determine the number of the waveguide, and then you can look up what frequency range that waveguide supports. So this one supports 75 to 110. Once you go to waveguide, you can do all kind of fancy things. For example, you can build a circulator. This is an interesting component. This is an even higher frequency. You can see how small the waveguide opening is. I think this is from 170 to 220. Oh no, actually it says, there you go. Its center frequency is 140 gigahertz, but it will work around that frequency range. So there's a magnet in here, and there's actually a warning here that says there's a magnet, and the magnetic field is designed to, I should say, guide the field that is allowed to flow through it. So this is port 1, this is port 2, this is port 3, and the signal can only flow in this direction. So the signal will only go from 1 to 2, from 2 to 3, but it cannot go from 3 to 2. So that's why it's called a circulator. Also a very useful component if you're doing some fancy measurements in waveguide. You can of course make antennas. Here's 2 examples of antennas. These antennas are so small because the frequency is so high. This is a WR10 antenna, which works from 75 to 110. And this is a D-band antenna, which I believe is 110 to 170. I'm not exactly sure. I have to measure the opening to know what frequency it is. But you can go really crazy up in frequency. Check out this guy. This is another waveguide, but look at how small that opening is. This is a 325 gigahertz antenna. So this thing will actually radiate out 325 gigahertz if you put a 325 gigahertz signal through it. So again, for very specific measurements, not many people build circuit in this frequency range, of course. And you can have all kind of bands, and this is an E band, you can have an H band, and so on and on, all kind of waveguide pieces. Waveguide pieces are fairly, they're less sensitive, but of course you can imagine that this edge of this connector is very sensitive. If it gets chipped or if it gets pushed, or if it changes shape, then of course it will not have the proper characteristic impedance, and it will have attenuations that are unexpected, and you have to be very careful with these. So as the last thing I wanted to show you is probes. These guys are probably the things that fall victim the most during measurements. They are extremely expensive. This is a 67 gigahertz GSG probe. I'll show you what that means. And these guys can cost several $1,000s, I think $4,000 or $5,000 for something like this. And if you make a custom-made one like this one, you're talking about $10,000 to $15,000. So you have to be extremely careful with these. So these are used in order to measure a circuit before it's placed in the package. So in a research environment, when you don't want to necessarily develop a package for your circuit before we can put it on the board and measure it, you can actually put your integrated circuit directly on the table and use this probe to come in and contact your circuit. The tip of a typical probe, for example, looks like this. Here's an example of that. This is a GSG probe, so the GSG just stands for ground, signal, ground. So the distance between these pins is something that you have to decide on when you're designing your circuit. So this one, for example, if you look carefully on the inside of the package, it says GSG. There it is. It says GSG and 100. 100 is the 100 micrometer is the distance between these pins. So from here to here is only 100 micrometer apart, so really close. We were talking about integrated circuits, and you bring these and you land them directly on top of your circuit. So your circuit, on your integrated circuit side, you place pads that are designed to accept this interface, and then you put this in a stable table and so on, and you bring it and then you land it directly on your integrated circuit, and that allows you to take signals in and out of your circuit. These things are also extremely fragile, and there is no way that you can actually see the tip, because the tip is so small that you cannot see. There's 3 wires at the end of that are only 100 micrometer apart. And this is a 67 gigahertz probe from Cascade. So if I were to take the plastic piece off at the end of it, you will see that it is using a V connector. There it is. This is a brand new probe. Very expensive, and you have to be extremely careful with this. Always use a proper torque wrench when you connect with this. Make sure you don't allow the connector to turn. Don't over tighten them, because these things will just break off, and then you can't really repair these, even though you can, but the repair cost is almost as much as a new one. So you might as well be very careful and make sure these things don't break. They do have a limited life cycle. You have to be very gentle with them. This is not something I can demonstrate to you on the website, on my website here, but make sure somebody who's done this shows you how to do them before you land your probe for the first time. So this one is from Cascade. You can also get them manufactured from other companies. This one is from another company called GGB. This is a completely custom made probe. It has many K connectors, so it has 1, 2, 3, 4, 5, 6 40 gigahertz connectors on it, and all of those wires end up at the tip here. So there is many wires here that land directly on the circuit. This is also 100 micrometer pitch. Very expensive because it's custom made, but GGB makes these things depending on what your configuration that you want. So be very careful with these things, and make sure that you use the proper connector and the proper cables, and you shouldn't put any weight on these. So if you have a cable coming out of this, make sure the cable doesn't put a lot of pressure here. Tape the cable in place so it doesn't bend the connector, because these are not designed to handle much weight. So here we are. We went through this whole bunch of connectors, components, and cables and so on, and this was just a very brief overview so you can appreciate or recognize some of the components that you come across in the lab. Always make sure you do this once with someone who's done it before, so you can take a look at how they do it and then learn the procedure and learn how exactly these things are supposed to fit together. And this was the first one that I wanted to make like this, and hopefully I'll make more videos where I show you more detail on some of the microwave techniques and so on, but there will be more. For now, this was just a quick thing to get you started. And if you have any questions, post it on the website or on the YouTube, and I'll try to answer them. And always be careful in the lab, and be patient. Patience is the most important thing. If you rush it, you're definitely going to break something. So, good luck.